Okay, a quick recap on the benedicts test. So, the benedicts test tests for reducing sugars. It contains, to start with, these aqueous copper 2 plus ions, which gives it its distinctive blue colour. And then, for a positive test, this copper is reduced from 2 plus to a +1 oxidation state, and then that gives that characteristic brick red precipitate here, which is copper oxide. In the copper oxide, it is a +1 oxidation state. Oxygen has -2 charge, so each of these coppers must be +1 in order to balance out the molecule and leave it with no overall charge. You can see here what's going on. So +2 to +1, and we get a precipitate. Okay, so these copper ions in the solution are in what we call a chemical complex, which just stops them from coming out of the solution as a precipitate too early for our need. And if we look at the 2 plus here and follow it across to where it goes into the precipitate here, so this is the precipitate, which looks like this kind of dark red colour. We can have a look. So oxygen has a -2 charge. This must be +1. So it's gone from +1 to from +2 to +1. It must have gained a negative charge or gained an electron here. So we call that reduction. Remember, so if you remember your oil rig, oxidation is loss, and reduction is gain. Okay, so this copper has gained these electrons to give it a +1 oxidation state. So that's why we say the copper has been reduced. It's gained electrons. The reason we call the reason that we call the sugars reducing sugars is because they're really good at providing these electrons here. So the sugar itself in the reaction will be oxidized because it produces electrons. So it's losing these electrons that are then used to reduce the copper. It's kind of complex, but I hope it makes sense to you now. So this is what you get with varying concentrations of glucose being used. So this is 0 or none. Here would be a small amount, medium, etc. and high. And because you get these varying colour changes, we can call it a semi-quantitative test. Okay, so we sort of get some quantitative data from it. Remember, we extended this by using we could use the colorimeter. For more accuracy. And the reason it was more accurate is the colorimeter is less subjective, which means that when you're doing the test, you choose the color change, and you could have you could say that the green is a small amount, but the colorimeter will give you an exact absorbance reading, and you could use one of your calibration curves to help with that. So you think about your calibration curves, they look like this. Sorry, you'd obviously use a ruler, but just for a quick sketch here. So here you'd have absorbance reading from the colorimeter, and so I don't know what the units are, so arbitrary units. And here you could make up a load of known glucose concentrations in percentages. And you could say that the absorbance perhaps goes up like this, which means that when you've got an unknown glucose concentration, you can find its absorbance, read along to the graph, come down, and you can give a pretty good estimate of the concentration. So it's semi-quantitative, it's not quantitative. And here's an example of the colours that you'd see for different percentage glucose concentrations here. Okay, so here's moving on to the non-reducing sugars. So we can see here water in Benedict's gives no reaction. As we would expect, glucose in Benedict's gives this copper oxide precipitate. It's a reducing sugar. It has reduced the copper 2 complex and turned it into copper oxide. But here with the sucrose, given the same treatment, no reaction. This is where the test for non-reducing sugars comes in. Okay, so we look at sucrose and we can see that it is a molecule made up of 2 sugar monomers, and it should be glucose and fructose. Both glucose and fructose on their own as the monomer, the single molecule, would be a reducing agent. So what we need to do to prove that we've got a reducing sugar in sucrose is we need to split this link and then retest. And if we split the link and retest, we know that the disaccharide we've got here, the sucrose, is in fact made up of 2 reducing sugars. So we can call it a non-reducing sugar, because in its normal state, before we do anything to it, it isn't reducing. But once we've reduced it, split it, we then get a reducing sugars as a result. So this is what happens here. We take the sucrose molecule and we break this linkage by adding water. So we'd call this a hydrolysis reaction. And in the test, we added dilute hydrochloric acid and heated. We then had to make sure the solution was alkali, so you needed an alkali solution for the Benedict's reaction to work, and I think we added sodium hydrogen carbonate for that. Now, once we've done this stage of adding the sodium hydrogen carbonate, we should then end up with the same test tube. So this would be the first stage for this. So this is non-reducing. So the first stage you'd have of the Benedict's and 2 centimeters cubed of the we know it's sucrose, and there is no reaction. The next stage would be to add 2 centimeters of your suspected sucrose and 10 drops we used of dilute HCl, which I think as was 0.1 molar. It's supposed to be a 3. And then we further on added sodium, hydrogen, carbonate until the effervescence stops. And that is just until the big fizzing stops, not any kind of small bubbles, otherwise you'll put way too much in and you won't see a result. So once we've done this, this should have hydrolyzed the sucrose. So this stage does this, it breaks the sucrose down into glucose and fructose. Don't worry about this at the moment, this is an enzyme, this isn't relevant to our discussion. So then you take your 2 centimeters of sucrose, which has been treated with HCl and the base or the alkali, and then you add 2 centimeters cubed, so that's equal volumes of the benedicts solution, and then heat in a boiling water bath for 3 minutes. When this is finished, if you have had sucrose, you will get a positive result and your solution will be a brick red due to the precipitate, which is the copper oxide precipitate. Or you could write that as Cu2O and then a little state symbol which says it's solid. Okay, so then the extension was that we took we had 2 test tubes. Okay, so the first one we had our glucose. So in this one we had 2 centimeters cubed of glucose and 2 centimeters of the benedicts, and then in the last one that we used we had 2 centimeters cubed of sucrose, 10 drops HCl and 2 centimeters cubed of benedicts. Both produced the brick red precipitate. Okay, so when we stick them in a centrifuge which spins them really fast, 3000 RPM, and pushes all the precipitate down to the bottom, why is it that we ended up with the glucose looking like it had this amount of precipitate? So this would be your glucose. But quite clearly the sucrose produced almost double the amount of precipitate. Okay. That is the question, that's the extension question. And when you think about it, if you go back to looking at the sucrose, we started off with a certain concentration of sucrose, okay, which was the same as glucose. So we started off with, let's say we started off with a 0.1 moles per decimeter cubed concentration of sucrose and a 0.1 moles per decimeter cubed concentration of glucose. So now we can do a little bit of investigation as to work out why it is we have double. So 0.1 moles per decimeter cubed is for the whole thing, but we had we only used 2 centimeters cubed of this. Okay, centimeters cubed is not decimeters cubed, so we need to make sure we convert our units for this little bit of chemistry we're going to do. So to get the amount of moles, it's concentration times volume. So we've got 0.1 times by 2 divided by 1,000, which is just turning the centimeters cubed into decimeters, and that will give us an answer. That equals 0.0002 moles. Okay, so that is the amount that we would have had in both the glucose and the sucrose. So how many molecules is there in 0.0002 moles? Well, we then need to use a number called Avogadro's number, which is 6.02 times 10 to the 23. That is how many molecules there are in a mole. Okay, so how many molecules there are in a mole. So we do this times by the amount of moles we've got, which is 2 times 10 minus 4. That gives us the amount of molecules that we'd have. And this comes out as a very, very large number still, 1.24 times 10 to the 20. So this is the actual amount of glucose or sucrose molecules we'd have. But if we come back and we look at what happens with the sucrose, although we started off with that amount of sucrose molecules, each sucrose molecule then produces 2 sugars capable of reducing the copper in complex. Okay, so we effectively double the amount of molecules that we've got in that test tube by carrying out the hydrolysis. Each one of those is able to form a complex with the copper. So instead of having 1.24 times 10 to the 20, suddenly you've got 2.48 times 10 to the 20 in one. Which is the sucrose, and 1.24 times 10 to the 20 in the glucose. If each one of these makes a complex, copper oxide as a precipitate, then you can see that the sucrose will produce twice the amount as the glucose, which is why we get a smaller amount in the glucose and double the amount in the sucrose. Okay, because sucrose breaks down into glucose and fructose, thus doubling the number of molecules that can form copper oxide. I hope that helps.